All right, in this example, we're told that we're going to take a 16 by 20 inch piece of cardboard and we're going to cut squares from the corners and then fold up the sides to make an open top box. And we want to figure out how we can do that and get the maximum volume. All right, what size of the squares should we cut out of the corners of the box in order to get the maximum volume? All right. So first thing I'm going to do, I need to draw a picture to get a feeling for what this looks like. Okay, so I've drawn a rectangle, and I know that the rectangle is 16 inches by 20 inches, and then I'm going to cut these squares, and they're going to be identical squares, right? Otherwise it really wouldn't hold up into a nice box. And I'm going to call those squares x by x, right? Because that's what I'm really trying to figure out is how big should those squares be in order to have the maximum volume in the box. Okay, so that gives me an idea. You can imagine cutting these squares away and then folding the cardboard along these dotted lines. You fold them up and that makes an open top box. All right, so we need to maximize the volume of the box. All right, so we need to know what are the dimensions of the box. So we need the length, width, and height of the box. Now when you fold these up, you can see the height is going to be the whatever x is, whatever the size of the squares we cut out. But we need the length and the width. All right, so the width here, we're going to take the 16 inches and we're going to cut away 2x, so 2 times x. So this width of the box is going to be 16 minus 2x, right? This width across the box. And then you can see the same thing for the length of the box. You know, it was originally 20 inches, and then we would cut away these 2 squares. So the length is, let's see if I can write this sideways. It'll be 20 minus 2x, right? 2x, right? That'll be the length of the box, right? So from across here, right? So the volume of the box, right? If we write an expression for the volume of the box, that's what we need in order to figure out how to maximize it. We need an expression for the volume. So we got length times width times height. Okay, so we're going to have 16 minus 2x times 20 minus 2x, and then times x. That's going to be the height. All right, so there's an expression for the volume of the box, and we want to maximize it, so we need to find the critical points, all right, which means we need to take the first derivative of it. In this form, I would need to use the product rule a couple of times to figure it out. So it would be much easier if I just multiply this out and make it into a polynomial. So that's what I'm going to do first, is just simplify this a little bit so it's easier to take the derivative of it. So I'm just going to FOIL these first 2 binomials, right? So I get 16 times 20, which is 320, and then take the inner, I get minus 40x. The product of the outer is going to be minus 32x, and then I take minus 2x times minus 2x, and I get plus 4x squared. Okay, but then I got to remember that's all times x. I still have this x out here. So I'm going to combine like terms, and I'm going to write the polynomial starting with 4x squared. Okay, and I can combine those middle terms into a negative 72x, and then I have plus 320, and then again times x. So then I'll just multiply everything by x. So I get 4x cubed minus 72x squared plus 320x. All right, now I've got a nice polynomial, and it's much easier to take the derivative of that. So I'm going to calculate the derivative of the volume. And so I'm just going to use the power rule. I get 12x squared minus 144x plus 320. And so to find the find the critical points, I need to set that equal to 0. Now it'd be nice to have it in factored form. So the first thing I see, I can factor out at least a 4 out of this whole thing. That still doesn't get me quite to a nice polynomial, but let's see what we got. We got 3x squared minus 36x plus 80. Okay. Now I'd like to factor this thing, but this just doesn't factor real nicely. So rather than factor it, I'm going to use the quadratic formula, right? X equals negative b. So again, the coefficients are a, b, and c. And I just need to find the points where this thing in parentheses is 0, right? So I'm just going to, so I got negative b, so negative 36, negative of that is positive 36, negative e plus or minus the square root of b squared, so 36 squared, minus 4ac, so 3 times 80, okay? And then all over 2a, okay? So I'm just taking the thing in the parentheses. So 2 times 3 is 6. Okay. And that's something I can put in my calculator and just get a couple answers, right? I get the plus and the minus version. So I get 9.055 when I use the plus. And if I use the minus, then I get 2.945. Okay. So those are a couple of different candidates for critical points, right? But I have to look at this carefully because if I look at my box is only 16 inches wide. So really, this x value can't be more than half of the box. So really, this x can only really be between 0 and 8. If I cut away more than 8, I can't cut away more than 8, right? If x is 8, I've cut away the whole box, right? So there's nothing left. It's just a sliver. It wouldn't really make a box. So this value here doesn't make any sense. So I'm going to cross that out. Okay, so really I only have one critical point here. And then I just need to evaluate that and figure out, is it a local maximum or a local minimum, or what's going on with that point. So in order to evaluate it, I'm going to apply the second derivative test just because we get a nice polynomial and it's easy to take the derivative of the derivative here. So if I take the derivative of the derivative, I get 24x minus 144. Okay. And then I can evaluate the derivative, the second derivative, evaluate the second derivative at my critical point, 2.945. So if I plug that in, what I got is a negative 73.32, which tells me it's concave down. Okay, concave down. So that tells me that my critical point is a local maximum. All right, so I have a local maximum here. Let me just write that down here. Local maximum. Local maximum at x equals 2.945. All right, so now we just need to evaluate all of our candidates for local min and local max. Now I think this is fairly straightforward. I mean, if I look at either one of these endpoints in the interval from 0 to 8, I mean, v of 0, volume at 0, if I have to cut away nothing, I can't fold up the sides and I have no volume, right? So even without putting that into my formula for volume, I know I'm going to get 0. Same way with 8. If I cut away the whole box, right, I'm going to get a volume of 0, right? Which you can see if you put it into the formula, this 16 minus 2x becomes 0, so the volume would be 0. So really, my only candidate for the global maximum is this 2.945. So I just need to calculate, what is that volume? What is the maximum volume? So I'm going to put it into the original function and calculate what that is. All right, I'm just going to put it into the original function for volume. And what I get is 420.11 cubic inches, right? And I know it's in cubic inches because my sides were in inches, so my volume has to be in cubic inches. So the maximum volume is 420.11 cubic inches when we cut away the squares of 2.95. So let me just summarize that down here. All right, so my conclusion is that the maximum volume is 420.11 cubic inches when we cut away squares of 2.945 by 2.945 from the corners. All right, that's all for this one, and I'll meet you in the next video.